Lisa McPherson here with A+ College Ready. One last time for Unit 4. These are the free response practice questions that appear towards the end of the PowerPoint for Unit 4 on atomic structure, spectroscopy, and periodicity. So again, like we did the multiple choice questions, I suggest that you take some time, we'll read the free response question, and those questions that appear on the slide, we'll pause at the end, give students an opportunity to talk amongst themselves and come up with reasonable answers. They might want to whiteboard some of these answers, that's a possibility, and then move on. The answers are in the next slide. So I've taken some large free response questions and broken them down so that you can stop after the questions and then only see the answers for just those questions on the next slide. So let's get started. First, we have a short free response question. Notice we have a table of first ionization energies for 3 different atoms, and we start with number 1, using principles of atomic structure and the information in the table above. Answer the following questions about atomic fluorine, oxygen, and xenon. So let me just talk about the stem of this question right here. Using principles of atomic structure. That means they want you to talk about effective nuclear charge, the charge of those particles, those plus nucleus, the minus electrons in the electron cloud, the attractive forces, Coulomb's law, looking at those Q terms. So you want to mention effective nuclear charge here. In addition to that, we want to look at the other term from Coulomb's law, that distance term. Remember, Zeph is one of those things we talk about as we move across a period, but as we go down a group, we're talking about distance because we're adding energy levels on, and so distance is a group trend explanation. So the first question says to write the equation for the ionization of atomic fluorine that requires 1681 kilojoules per mole. So let me just draw your attention to that. They're not asking you to do any calculations. They want a chemical equation showing how when 1681 kilojoules per mole of electrons are removed, what does that look like in a chemical equation format? So they want you to write that equation. Now, what are they asking you in question B? It says account for the fact, that's the same thing as justify, explain, etc., that the first ionization energy of atomic fluorine in the table is greater than that of atomic oxygen. Notice it says you must discuss both atoms in your response. On the AP exam, they will expect that, but they may not remind you of that. So that in your response, you must mention fluorine and oxygen both, and you need to justify why the first ionization energy of fluorine is greater than that of oxygen. And finally, question C. Predict whether the first ionization energy of atomic xenon is greater than, less than, or equal to the first ionization energy of atomic fluorine. Now, if you know your periodic trends, you can probably figure this out pretty quickly, but then notice you have to justify your prediction. So depending on whether this is a period issue or a group issue or some of both, you will need to mention that effective nuclear charge, or you're going to need to mention energy levels or something in your justification. So pause the video here, talk amongst the folks in your group, y'all come up with a reasonable answer, and then we will move on and check those 3 answers. Okay, so you can see here at the top of the slide the equation for the first ionization of atomic fluorine. Well, what is ionization? It's when we're removing an electron. So an electron is going to come off of this and it's going to leave this ion. Notice they do mention that it's gaseous because the definition for ionization energy is for an element in its gaseous state, but phase designations are not required, and so that they don't really care if you just had F instead of F as a gas, but they do want you to show that this positive ion is being formed and an electron has been removed. And this feels uncomfortable for a lot of people because you're not used to seeing F with a plus charge, but that's why it's got a really high ionization energy. It doesn't want to give away that electron, it wants to gain them. But this can happen if you apply enough energy. So there's your correct answer for 1 point. For part B, account for the fact that the first ionization energy of atomic fluorine is greater than oxygen. So notice it says 1 point is earned for recognizing that the effective nuclear charge of fluorine is greater than that of oxygen. So if you said the Zeph of F is greater than that of oxygen, and that justifies the statement, that's fine. A lot of times in these scoring rubrics for free response questions, they get a little bit more verbose than you need to. So take a look at what earns the point. And if, say, for example, maybe you're swapping papers, you're grading each other's responses, that's a good activity to do to get used to seeing what these AP answers should look like. Look, did they mention fluorine and oxygen in their answer? And did they mention that the effective nuclear charge of fluorine is greater than that of oxygen, and that causes the first ionization energy of F to be greater than that of oxygen? And for C, predict whether the first ionization energy of atomic xenon is less than, greater than, or equal to the first ionization energy of atomic fluorine. So that's that blank space or the question mark in our table, and justify it. So 1 point is earned for a prediction based on size and or energy level. Unfortunately, in this presentation mode, some of that rubric is being cut off. So I'm going to have to take a look at this and see what else is in the rubric. Okay, upon further inspection, this particular grading rubric says that 1 point is earned for a prediction based on size and or energy level. However, that doesn't really make sense with the way the question was asked, because it does say you have to justify. It's possible that on the AP exam, a question like this might be a 2 point question. They might give you a point for justifying separately from your prediction. I really, though, suspect that if you predict correctly, which that means you've just memorized what the trend is, they probably won't give you the point if your justification is not correct. So I think the point's going to be associated with justification. So if we take a look at where fluorine is in the periodic table compared to xenon, they are not in the same period and they're not in the same group. But what's the really big difference here? Well, xenon is like 3 more periods down from fluorine. That means it has 3 more energy levels than fluorine does. And also, it is a noble gas. And so it says the first ionization energy of xenon should be less than the first ionization of fluorine, because you got to remove electrons from the fluorine atom that are much, much closer to the nucleus, and therefore held on much more tightly and require a lot more energy to remove than those way out at the edge of xenon in the 5p energy level. You don't probably need to be so specific as to mention the energy level, sublevel, orbital, etc., like they did here in this answer. I think it's sufficient enough to say that xenon is in period 5, whereas fluorine is in period 2. The electrons, the first electron removed from xenon is much farther from xenon's nucleus than the electron that is removed from the fluorine atom, and therefore the ionization energy should be much less for first ionization energy, much less for xenon because of distance from the nucleus, because we're really looking at sort of down a group pattern, and that's a distance from the nucleus justification. Okay, now this is a longer free response question, and it's going to be broken down a little bit differently. Okay, so when answering this particular free response question, you're going to break it down into 3 smaller parts. You'll notice that we have parts A, B, C, D, E, and F. And on subsequent slides, I'll have the answer to A and B, and then the answer to C and D, and then the answers to E and F. So let's just talk about A and B first. So here we have a table with some successive ionization energies for some unidentified elements. It shows the first 3 ionization energies for atoms of 4 elements from the 3rd period of the periodic table. The elements are numbered randomly. Use the information in the table to answer the following questions. Which element is most metallic in character, and explain your reasoning. And then They want you to identify element 3 and explain your reasoning. So pause the video here, and when we come back, we'll talk about the answers to A and B only. Okay, so we didn't really talk about metallic character per se as one of the periodic trends, but I can tell you this, it's based on, well, not based on, but it's the same trend that reactivity is. Remember we said the most reactive metal is francium, and the most reactive nonmetal is fluorine. The F's at opposite corners of the periodic table. And metallic character, from terms, we're looking at electrons and reactivity, the closer you are to group 1 to the left edge of the periodic table, the lower your ionization energies are, the more easily it is to remove electrons, and therefore you have higher metallic character over there. So the element with most metallic character is going to be the one that's in group 1 or closest to the left, that has the fewest number of valence electrons. So maybe that helps you. And then identifying what element 3 is, they really want you to notice that this is the third period of the periodic table. So when you look at element 3, you look at successive ionization energies, what can you tell about element 3? Can you tell me how many valence electrons it has? If so, you would know what group it's in, and you already know it's in period 3. So see if that helps a little bit. Okay, so the answers are A, element 2 has the most metallic character. It has the lowest first ionization energy, and metallic elements lose electrons when they become ions. And element 2 requires the least amount of energy to remove an electron. It also, you can see from successive ionization energies, it has only one valence electron. So notice you get 1 point for identifying that element 2 is the answer, and then also 1 point for talking about those ionization energies. So I think you could justify it either way. Let's look back at the question. You could justify it by either saying that element 2 has the lowest of the first ionization energies, so that means its valence electron is the easiest one to remove, or also it clearly is the one that has just one valence electron based on successive ionization energies, and that's going to be the farthest to the left. It's going to have the most metallic character. B, identify element 3. Element 3 is magnesium, so you get 1 point just for figuring out that element 3 is magnesium. Second point is earned from your justification or reasoning. And element 3 has a low first and second ionization energy, so the increase in ionization energy is fairly modest, but the third ionization energy, there's a big jump there. So that indicates that this element has only 2 valence electrons, and since these elements are in the third period, we know that magnesium is our only reasonable choice. Okay, so let's go back. And by the way, this 8 points possible up here at the top is for all of question 1, not just A and B. Okay, so we're going to look at C and D now. So C says write the complete electron configuration for an atom of element 3. Then, what is the expected oxidation state, think charge, for the most common ion of element 2? These should be relatively quick, but pause, write down your answers for those, and then we'll move on. Okay, so answer C, before I reveal what the answer is, let me just say that this is based on what you said in part B. So on the AP grading rubrics, the way that this works is what if you identified element 3 incorrectly? You said it was calcium, or you said it was silicon, or something like that, and you got it wrong. But then you wrote the electron configuration for what you thought element 3 was. If you said this was silicon, for example, and then you wrote a correct electron configuration for silicon, you would actually get that point. Even though it's the quote-unquote wrong answer, it's still right based on your previous wrong answer. Okay, so the lesson learned here is don't ever give up on free response questions, because you may have something that's very difficult to answer and you think, oh, I can't possibly answer anything else here, it's just going to get worse. No, they don't. A lot of times in a free response question, like here, A and B may be pretty challenging. And then C and D, wow, those are pretty easy. So let's take a look at the answers for C and D. Okay, well, we'd said that for magnesium, magnesium was element 3. There's the electron configuration. Notice if you drew arrows, that would be wrong because that's not the electron configuration. That arrows would have been orbital notation. Okay, so you need to make sure that you've got your types of electron configurations down. Then, what is the expected oxidation state for the most common ion of element 2? Okay, so what did we say that um, uh, element 2 was? Is element 2 was the element with most metallic character, right? And so that's going to be the one that's in group 1, that's sodium, and sodium's most common ion is +1. Again, this is a place where you could earn an easy point even if you misidentified element 2. What if you said element 2 was chlorine and then you put -1 here? Well, that would be right. You would get the point for a chloride ion usually is a -1. Not always, but it's the expected state, oxidation state. So again, don't give up. Keep working. Let's go back to the question and give you guys a chance to work on E and F. Okay, so again, pause the video here, write your answers for E and F, and then we will check those answers. Okay, so E, what is the chemical symbol for element 2? Well, okay, so this is going to assume that you've correctly identified what element 2 is, and element 2 is sodium, most metallic character. But remember, well, I guess if you're identifying element 2 incorrectly in D, if you wrote the right chemical symbol for whatever you chose for D, you could get this point. And then F, a neutral atom of which of the 4 elements has the smallest radius? So you got to think about atomic radius across a period, what's happening to that, and then you got to figure out how do you order these 4 elements from left to right across this period. So let's take a look at those answers. Element 2 should be identified as sodium. Know your element symbols, don't forget those. And a neutral atom of which of the 4 elements has the smallest radius? Element number 1, 1 point for each of these. So why is it element number 1? Let's go back and look at that, okay? Well, what do we know about atomic radius? We know these are in the same period, period 3, and as we move across a period from left to right, what happens to atomic radius? Snowman fell down. Oh, atomic radius gets smaller. So the element with the smallest radius is going to be the one farthest to the right in the period. Okay? And so because if we look at first ionization energies, remember Zeph, or effective nuclear charge, is increasing as we go across the period. So as you go across the period, it should get more and more difficult for you to remove that first electron. So your first atom should be element 2, followed by element 3, then element 4, and with the highest first ionization energy, greatest Zeph, would be element 1. This element would be the one farthest to the right and therefore have the smallest radius. Okay, so now we have free response question number 2. Answer the following problems about gases. So we have a table where we have 2 isotopes of neon and the masses of those 2 isotopes. The average atomic mass of naturally occurring neon is 20.18 atomic mass units. There are 2 isotopes, common isotopes, of naturally occurring neon as indicated in the table above. Using the information above, first calculate the percent abundance of each isotope. When you've completed that, calculate the number of neon 22 atoms in a 12.55 gram sample of naturally occurring neon. So it's going to take you a little while. Pause for a while, and then we're going to come back. So we got 2 different calculations. Y'all might want to split this up in the room. Maybe one side of the room calculates the percent abundance, maybe the other side calculates the number of neon 22 atoms, and then you can come together and show each other your work. That might be one way to attack this. So pause and then come back for our answers. Okay, so hopefully you can read this. If not, maybe the teacher can zoom in on this a little bit or rewrite it someplace else. But these are calculations that you should have done before. In the first question, we only get 1 point for doing this correctly. So here we're going to let X represent the abundance of neon 20. It could be the neon 22. It doesn't matter which one you assign X, as long as the abundance of the other isotope is 1 minus X. So remember, all your percentages are converted into decimal equivalents. So if you take like 40% at 0.4 and 60% at 0.6 and add up 0.6 and 0.4, you get 1, not 100. So that 1 is the decimal equivalent of 100%. So we've taken the atomic mass of neon 20 times its abundance plus the atomic mass of neon 22 times its abundance at 1 minus X. And they've given us the average. So then what we have to do is be careful with our algebra, because especially you're going to come up with 2x terms and you're going to need to do this subtraction. Also watch your negative signs, because remember, this is a percentage abundance. It's not going to come out negative, folks. Okay. And then once you find out what X is, multiply that by 100 to get the percentage of the neon 20, and then subtract that from 100, and that will give you your percent abundance for neon 22. Notice it said calculate the percent abundance of each isotope. So if you just calculate the percent of one, you're not going to get the point. You've got to do both of them, and those percentages should add up to 100%. In our second calculation, we're to calculate the number of neon atoms. Anytime they mention calculating the number of atoms or protons or electrons or whatever, they're talking about particles, and you're going to have to use Avogadro's number somewhere in there. We're starting here with grams, and in chemistry, what do we do with grams all the time? You got it. Change it to moles. So grams to moles here. Now, this is the part that's not quite so intuitive, is that 1 mole of neon, a whole sample, is only 9.5%. So you've used this number from the previous problem. This happens in AP all the time. You've used this number in this problem here, and because only 9.5% of the whole sample is neon 22. And then once you figured out how many moles of neon 22, not moles of all the neon, but just that isotope you have, then you can convert those moles into neon 22 atoms. So it's a little bit tricky. Notice also you can't use 9.5. You have to use its decimal equivalent in the calculations. Not 9.5, but 0.095 is the percentage. Notice everything else cancels, and you get 3.6 times 10 to the 22 atoms. If you have a kind of normal, average, everyday sort of number, like 12.55 in grams, and you're converting that to atoms and stuff, this number should be huge. So if this number isn't really big because of Avogadro's number, something's wrong. Now let's look and see where you get points here. 1 point is earned for the correct molar mass. All right, that's an easy point. So even if you have no idea how to solve this problem, make sure you change grams to moles, folks, because that's a point. Another point is earned for the correct fraction. That's this term right there, the correct fraction of neon 22 in neon. And then finally, another point is earned by determining this number of atoms right here. So that means you have to get this conversion factor in there correctly. Okay? So let's move on and see what else we've got. All right, so this is part B of free response 2. A major line in the emission spectrum of neon corresponds to a frequency of 4.34 times 10 to the 14th inverse seconds. Calculate the wavelength in nanometers of light that corresponds to this line. So again, let's take a pause. Be careful with your units. I'm going to help you out here just a sec. Remember, frequency, a lot of times they say it's in hertz. Inverse seconds in hertz is the same thing. The other thing is be careful. They want the final answer to be in nanometers. Go. Okay, so here we have the answer to question B. And we've taken this equation, this light equation, speed of light is equal to wavelength times frequency, and algebraically rearranged it to solve for the unknown. Calculate wavelength, we've solved for wavelength. Wavelength is equal to the speed of light divided by the frequency. But notice what's going to happen here. When you perform this calculation, these inverse seconds are going to cancel, and your wavelength will be in meters. And that's not what they asked for. They want nanometers, right? So we have to go over here and we have to cancel our meters and end up in nanometers. So you got to have this conversion factor in here. And I remember nano, 9, 10 to the minus 9, or 10 to the 9 nanometers in a meter for that conversion factor. And so then you're going to get 690 nanometers. 1 point is earned for the correct setup. So if you just put these, did the algebra right and put the numbers in the right place, you're going to get a point. A second point is going to be earned for getting this actual answer in nanometers. All right. Okay, so here we have part C of free response question number 2. In the upper atmosphere, ozone molecules, that's this O3 right there, decompose as they absorb ultraviolet light. Radiation is shown by the equation below. Obviously, you don't see the light in there, but they're telling you that UV light makes this decompose. Ozone serves to block harmful UV radiation that comes from the sun. So way up there in the upper atmosphere, ozone is our friend. Down here, surface of the earth, not so much. That's smog and air pollution. But we like it out there blanketing the earth. A molecule of ozone absorbs a photon with a frequency of 1 times 10 to the 15th inverse seconds, or hertz. Okay? So here's your questions. How much energy in joules does the ozone molecule absorb per photon? Okay? And then the minimum energy needed to break an oxygen-oxygen bond in ozone is 387 kilojoules per mole. Does a photon with a frequency of 1 times 10 to the 15 inverse seconds have enough energy to break this bond? Support your answer with a calculation. Okay, so this one's a little bit tricky, particularly the second part of the question. Pause, discuss, come up with answers, and we'll check them. Okay, you'll be glad to know this is the last free response question that we're going to do. So let's take a look at the answers. First, how much energy in joules does the ozone molecule absorb per photon when we are only given that frequency? So here we're going to use E is equal to h nu. Again, that's in your constants and equations page. And so the energy of that photon is equal to Planck's constant, okay, times the frequency of that photon right there. So let's take a look at units, which are going to be very important in a minute. This inverse seconds and seconds right there cancel out, and we're left with joules. But again, notice the way that this question's worded. How much energy in joules does this molecule absorb per photon? That's going to be important here in the second part. So notice that even though we only have joules left over from the units canceling, this is joules for 1 photon. 1 point is earned for the correct answer. Now, if you just put joules, that would be the correct answer. The per photon becomes important for the second question. Okay, so the second question says the minimum energy needed to break an oxygen-oxygen bond in ozone is 387 kilojoules per mole. Does a photon with this frequency have enough energy to break this bond? Well, the energy we've calculated for that photon with that frequency is 6.63 times 10 to the minus 19 joules per individual photon. So we start with that. But here, they're talking about per mole, okay? And so we need to change photons, joules per a single photon, to joules per mole of photons. And this is going to be the tough part. And notice once you do that, then photon cancels, and this we're calculating the amount of energy that a mole of photons would have. But again, we're going to have to compare it to kilojoules per mole. So instead of joules per mole, we need now this second conversion factor so that joules cancel, and we're left with kilojoules per mole. And what we get here is 399 kilojoules per mole. So if you have a photon with that frequency, it's going to have enough energy. It's going to, if you have a mole of them, it's going to give off or have enough energy to apply to bond breaking of 399 kilojoules per mole. So that calculation earns you a single point right there. Then comparing your calculated value to this 387 kilojoules per mole required to break the bond, because you have more energy than is required to break it, the bond can be broken. So you would earn a second point here. Now, don't be too terribly discouraged. What if you just totally bomb this and this answer is completely wrong? Let's say you get 5, okay? And you say, oh, but 5 kilojoules per mole is less than 387 and the bond cannot be broken. Well, you're not going to get this point right there. But this one, if you compare the amount of energy, wrong as it may be, to that 387 kilojoules per mole required to break those bonds, if your comparison is correct, you draw the right conclusion based on your comparison, you can earn that point. Okay, and this AP exam is a game of individual points. That the difference between a 2 and a 3 is just 1 point. So keep going. Do not give up. Just remember, you can't go anywhere except for right where you are taking that test. There's nothing else to do other than to earn those points. So best of luck. End of Unit 4.